All right, so 5.4 is modeling and optimization. All right, so we're going to start out with a strategy for these problems, and then we'll work through a few. We'll just get through as many as we can today, and then we'll just pick up tomorrow with whatever's left. So the strategy for max and min problems. All right, so first is to understand the problem, because you can't really do anything if you don't know what it's asking you to do. Two is to develop a mathematical model of the problem. Three is to graph the function, which we will do, but with that, know that also can just mean draw a picture, okay, of what's going on. Okay, the draw a picture kind of comes in with 2 and with 3 because you kind of need to see what you're looking at in order to be able to actually develop the model. So 2 and 3 can kind of go interchangeable in a sense, but you can't graph a function if you don't have one written out. So anyways, just know that those two kind of go hand in hand together. 4, identify the critical points and endpoints. Five, solve the mathematical model. And then lastly, interpret the solution. I'm going to go ahead and write out what the problem is. I think some of them that are really long, I may not write out the problem, but this one's not too bad. So this one is a maximizing area problem. So it says, what is the largest possible area for a right triangle whose hypotenuse is 5 centimeters long, and what are its dimensions? All right, so understanding the problem, okay, it's asking us about the largest possible area, okay, and then it also wants to know the dimensions. So I'm going to go ahead and draw a picture. I'm going to have a right triangle. We're told that the hypotenuse is 5 centimeters long. But I don't know yet what the other two sides are. So I'm going to have X and Y. So a lot of times with these problems, what ends up happening is you write out formulas that look like they could pertain to it. You find formulas that you have the information for, and then you basically solve them that way. So we know we're looking for area. So in general, what is the area of a triangle? Okay, 1/2 base times height. So yeah, so it's going to be, in our case, 1/2 x times y. Okay, when we have a triangle, what's another formula that a lot of times we deal with, specifically a right triangle? Not quite what I'm looking for, but that is true. I want something I have all the pieces for, or that I have a lot of them for. Huh? Okay, Pythagorean theorem would be what in our case?
Y squared plus x squared equals 5 squared equals 25 squared.
And so I have two formulas now that I have the pieces for. Okay, if it had given me an angle, Sarah, I could have used that route. I don't know what those angles are, which is why I can't do that other than the 90-degree one. So I want to solve for one of these variables that I can use to plug in here. So I'm going to do y since I wrote that one first. So y is equal to 25 minus x squared. And we take this square root of that whole thing. Oh, I couldn't see who it was. I just saw an arm. All right, so now I can take this here and plug it into my area formula for y. So I would have area is equal to 1/2 x times the square root of 25 minus x squared. And then as another way that I can write a square root, I can write it as the power of what? Okay, so I can rewrite it as 25 minus x squared raised to the 1/2. Now you may be thinking, why in the world did I just do that? Like, whatever. Well, we're going to be taking the derivative, so it makes it a little bit easier, in my opinion, if it's in fraction form to think about. So I want to take the derivative of this. But what do we notice that we have here? I have two things specifically that I notice when I look at this in regards to the derivative. Well, they are squares, but that's not what I'm looking for. I'm talking about the derivative. What two rules do you see?
I see product rule and a chain.
Okay, a product rule and a chain rule. So I'm going to have to keep both of those in mind here as I go. Okay? So the derivative of area with respect to x is 1/2. Now, I'm going to save the easier part for last. Okay, I'm going to deal with this chain rule as part of the product rule first, okay? So 1/2 x times, okay, I'm going to pull this 1/2 out front. So this is going to be 1/2 times 25 minus x squared raised to the negative 1/2. Then I need the derivative of the inside of this, which is minus 2x. So that's taking care of this piece. So now I can do the easy part of the product rule, which is going to be just plus 1/2 times 25 minus x squared to the 1/2. And this is all going to be equal to 0. So I want to solve for x, which looks a little bit entertaining as it sits. So I'm going to move some stuff around. Slide this up some so that you can see it. All right, so looking at this, okay, I'm going to do this next step in a different color just to help see what's going on. This 1/2 and this 2 can cancel each other. The power of negative half is going to move that square root to the bottom. Okay, this one. Okay, this x is going to be on top. I've got this x that's going to stay on top. I've got a negative sign with it. And then this 2, because it's a half, is going to be on the bottom. Okay, so this is going to be on top, negative x squared over, on the bottom, I have 2, and then the square root of 25 minus x squared. So that's taking care of that first piece. And then, find another one, purple. For this piece, I'm going to have this staying on top and just the 2 on the bottom. So I'm going to have the square root of 25 minus x squared all over 2. And this whole thing is equal to 0. Couple different things that I could do here to proceed.
How do you get the second half of the derivative?
This part,
Yes.
it's the product rule.
Okay.
So I took the derivative of x. So I did it backwards, but I wanted to do the harder part first.
Okay.
Just, yeah. Usually I do it the other way, but I was like, let's do the harder part first. So what I'm going to do now is I'm going to move this piece, because it's negative, over to the other side. I could get a common denominator, combine things, blah, blah, blah. But in the long run, I think that's going to make the work a little bit more difficult, because you're going to have to do like multiplying by a square root and all this other stuff that actually is going to work out kind of nicely for us. So I would end up with, go back to just red for this now. So I would have the square root of 25 minus x squared over 2 is equal to x squared over 2, and then the square root of 25 minus x squared. So I obviously ultimately want to get things simplified down. So if I actually multiply by this square root here, okay, this one over here, then that will cancel stuff out for me. Okay, it's going to cancel the square root because square root times square root stuff inside just comes out. So 25 minus x squared over 2 equals x squared over 2. Okay, multiplying either direction by 2. The 2's are going to cancel out for me on that. So I'm going to be with 25 minus x squared is equal to x squared. I can add this x squared over. So I would have 25 equals 2x squared. Divide by 2. I'm going to put the x back on the left. So x squared is equal to 25 over 2. If I take the square root of that, x is equal to 5 over the square root of 2. Now you may think, okay, well normally square roots when we're solving them are plus or minus, but I'm doing stuff with area and all of that, so I can't have a negative value, can't have a negative side length, okay, because then I can't have area, so that's why I don't have the negative option. Don't want the radical on the bottom, so finally this would be x is equal to 5 root 2 over 2. Well, all right then. Now, due to the nature of how these problems work out and how we had x squared plus y squared is equal to 5 squared, okay, we could have done this problem the same way, but we could have said x is equal to blah, blah, blah. So this is going to also imply that y is equal to this. So these are the dimensions, okay, of the side. But it also, the big thing that it wanted me to do was area and dimension, so I need area. So area is equal to 1/2 x times y for our particular case, so 5 root 2 over 2 times 5 root 2 over 2. So that's going to give me 25 times 2 on top over 8 on the bottom, which is going to give me 25 over 4, which reduces down to be something like 6.25 for my area. So now that one didn't require graphing, didn't require critical points. We just had to set it up and solve it, okay, with the derivative setting it equal to 0, blah, blah, blah. I guess in reality those are critical points, but probably don't think of them that way in this sense. Okay, that problem took ridiculously long.
Square root throw away. Oh, never mind. I thought. Never mind. Just 2 square root 4.
All right, let's see if we can get through one more. This one should be a little bit faster. The math's not as hard on the next one. Not that math was necessarily hard, but. All right, so this one is another area problem. It says show that among all rectangles with an 8-meter perimeter, the one with the largest area is a square. Okay, so in this case, we are given perimeter. Okay, and we want to show that the one with the largest area is a square. So, what is the perimeter of a rectangle?
2L plus 13.
2L plus 2W. Okay. We're told that the perimeter is 8 meters, so I can take that and make that an 8. Both of these have a 2 in them, so I can rewrite this as 2 times L plus W. So then 4 is equal to L plus W. And then I need to solve for one of the variables. Doesn't really matter. Let's just say W is equal to 4 minus L. So now I want to find area, okay? Area, I could have written this at the beginning, got ahead of myself. Area of a rectangle is equal to what? Length times width. So now I can replace width with 4 minus L. So L times 4 minus L, which is 4L minus L squared. Now I want to maximize area, so I am going to take the derivative, so A prime is equal to, what's the derivative of that? 4 minus 2L, and we're going to set that equal to 0. So what does L equal to? 2. So then we can do our little sign chart. Okay, for the derivative. So if I put in 1 into the derivative, so into A prime, what do I get? Or 0 for that matter, it doesn't really matter. Plug it into the derivative, so the 4 minus 2L. So if I made L 0, it'd be positive. If I made L 3, it'd be negative. Okay. So, with that, okay, I can go back over here and solve for W. W is equal to 4 minus 2. So W is equal to 2. Oops. This was what we plugged in over here, just for reference. Okay, so then now area is equal to length times width, which is 2 times 2, which is 4 meters squared. So that tells you that by finding these side lengths like this, that tells us that the rectangle with a perimeter of 8 meters the area of that is going to give you, to get the max area, it has to be a square. So, let's see. Do I think we could get... Let's go ahead and write the problem for the next one, and then we'll see how much time's left if I think we can get through it. Number 6. These ones are getting a little bit more difficult. A rectangle has its base on the x-axis and its upper 2 vertices on the parabola y is equal to 12 minus x squared. What is the largest area the rectangle can have? And what are its dimensions? Try to get at least the picture set up for this one, and then may have to actually solve it tomorrow. We can actually talk about it. All right, so this one doesn't give us that much information. Okay, we know that it's a rectangle. We know that its base is on the x-axis, meaning I've kind of got to graph this. The other thing that I know is that I have a parabola. Okay, I don't know if you remember back from Algebra 2 how to graph a parabola, but the fact that it has a negative sign in front means that it's upside down. Okay, so it's an upside down U. And then the 12 moves it up 12 places. Okay. So I'm going to deal with the parabola first, and then I'll deal with the rectangle part after that. So I've got this parabola here. We're just going to make this up. So we're going to call that 12. We are told that the rectangle has its base on the x-axis. So, and we know that the top vertices have to intersect the parabola. Okay? Can intersect anywhere, but we know that it has to intersect. Okay, so we've got our rectangle there. And that's really all the information that I know. Okay, so I'm going to say that from y-axis to the side of the rectangle has length x. Okay, and then on the other side that it's also length x. Making this entire thing from here to here. Oh, it kind of looks like a little smiley face guy. Making that entire thing 2x. That's true. With little glasses on. Like, wee, little glasses. That might have made it worse. I think that made it worse. Oh well. Nice little character. It's supposed to be his little glasses. He doesn't have an ear. Just like, anyways. Okay. Whatever. Sidetrack. Okay. We would say then that this point occurs at x and then 12 minus x squared. Okay, so whatever x is equal to, we plug that in, and that's going to give us the y value, okay, in that equation. So we know that I'm going to set up as much of this as possible, and we'll go back and kind of finish it tomorrow. But we know the area of a rectangle is length times width. Our length, we can say, is this 2x value. And then our width is from here to here, okay, which is going to be 12 minus x squared. We might get through this. Probably not, though. So then I can multiply this through. That's going to give me 24x minus 2x cubed. So then now I would take the derivative of this, which would be what?
24 minus 6x squared.
24 minus 6x squared. Setting this equal to 0 and solving for it. So I would have negative 6x squared is equal to negative 24. X squared is equal to 4. So x is equal to, again, normally taking the square root would be plus or minus. Can't have negative values with area. So it's just going to be the positive 2. So I want to know what the largest area the rectangle can have is. So I'm going to take and plug this stuff back in to this original area equation here. Okay. So area is equal to 2 times x is 2 times 12 minus 2 squared. So that's going to be 4 times, let's see, 12 minus 4 is 8. Do what?
Where did we get that first? Oh, I see.
From the
Okay.
12,
And
2x.
the x is.
Yep.
Okay.
So this is 4 times 8. 12 minus 4 is 8. So that's going to be 32, okay, units squared is the area. Okay, it also wants the dimensions. The dimensions are just each individual piece. So 2x is going to be 4 by 12 minus 2 squared is 4, so that'd be 8. So the dimensions, it would be a 4 by 8.
Oh, okay, because you plugged the x back in.
Yep, so you just plug it back in, and then we treat this as 2 separate pieces. So that, the 2x is what's giving me the 4. Okay, and then the, I don't know if it's, okay, it's going to show up. Then the 12 minus x squared is giving you the 8 when evaluated at x is equal to 2. So that would be the rectangle with the largest area, and that would be the dimensions of that rectangle. All right, so we did get through that one. I didn't know if we were going to have time because that can be kind of a long problem. So we'll be done for today. Bell's about to ring, and then we'll pick up tomorrow with a couple more of these types of problems because, like I said, tend to like this stuff on the AP test.